Today we're going to continue talking about trigonometric substitution. The thing that we want to add to this today is the integration step, where we integrate g of theta into our theta antiderivative. So we're going to want to talk about integrating the theta integral into the theta antiderivative. We've been spending some time deciding on what products of powers of trig functions can be done with substitution. We want to be able to recognize these because when we get to the theta integral, if the theta integral is a substitution, if there's a substitution in the theta integral, then there was a substitution in the x integral. So we stop, go back and get the substitution in the x integral. That's the point that we want to make today. So let's take a look at an integral that can be done by substitution and see how that shows up in our theta integral. So let's suppose we wanted to integrate x times the square root of 9 plus x squared to x. This is a substitution integral. W should equal 9 plus x squared. Let's pretend that we didn't see that. Let's pretend that we didn't see that the derivative, if w is 9 plus x squared, then our dw is this x right out in front. Let's pretend that we didn't see that and just read this as a trigonometric substitution. You like to think that wouldn't happen to me. I would notice that substitution right away. Trust me, on the day after we start talking about trig substitution, if I give you this integral, I don't care how good you are at substitution, you would go for a trigonometric substitution. All I'd have to do is put this one first on the quiz. I wouldn't even have to call the quiz trigonometric substitution. I would just have to talk about trigonometric substitution on Monday, give you a quiz on Tuesday with this one first. I could even call that quiz substitution. And you'd be like, oh, trig sub. That's how awesome trig sub is. I know you all love it, but it's not going to be necessary in this problem. All right, so let's go through our decisions. This 9 plus x squared, this is what's going to tell us the case. We see there's a quadratic running around. So we're going to say that this is the tangent case with a equals 3. So our substitution will be 3 times the tangent of theta. I think I was using 5 all day yesterday, so yeah, well. Today is brought to you by the number 3. The other pieces that we're going to need are a dx, because we're doing a substitution. The derivative of 3 tangent theta is 3 secant squared theta, d theta. The other piece that we're going to need is that 1 plus tangent squared is equal to secant squared. That's why we're making the substitution 3 tangent theta, so that we could use so that this 9 plus x squared will become 9 plus 9 tangent squared, and I can replace all that with 9 secant squared. That's the whole point of doing the trig substitution. And we're going to pretend that we didn't notice that this should be a regular substitution problem. Let's substitute our things. The x has to get replaced with 3 tangent theta. Then we'll have the square root of 9 plus 3 tangent theta squared. And then the dx is 3 secant squared theta d theta. Now the trigonometric substitution thing happens. This square root of 9 plus x squared, that became the square root of 9 plus the square of 3 tangent theta. Is 9 plus 9 tangent squared theta, which is the square root of 9 secant squared theta. And the square root of 9 secant squared theta is 3 secant theta. So our theta integral, if we gather everything up, I'm going to write it down one more time. So I've got the 3 tangent theta. I've got this 3 secant theta from the square root part. And I've got 3 secant squared theta, d theta, from the dx. Those are all my pieces. So if we simplify all of this, I'm going to gather the 3's, although 3 3's is 27. And then we'll have a secant cubed and 1 tangent. Now we've arrived at the theta integral. We have done our trigonometric substitution. We have landed on our theta integral. Now we've got to think of how to integrate this integral. This integral is going to be a substitution integral. I've got secant cubed tangent to the first. Notice if I make w equals tangent, then dw is secant squared, but that leaves only 1 secant left over. There are 3 secants there. To make the substitution w equals tangent, I would need 2 copies of the secant to be the dw. That leaves 1, but we only can convert those in pairs. So tangent is not the substitution. So we can try secant. If w equals secant, then dw is secant and tangent. So I'll save 1 factor of secant and 1 factor of tangent to be the dw. I have that here, so that's the substitution I want to make. The substitution w equals tangent theta is not going to work because I can't convert 1 factor of secant to tangent without introducing square roots, which is what we're trying to avoid in the first place. At this point, we should stop. We should say, hang on a second. If the theta integral is substitution, that means the x integral is also substitution. And we're wasting effort to do trigonometric substitution on this. So this is the point when we recognize we should stop. If the theta integral is substitution, then our x integral is substitution as well. So we should stop, we should go back and redo the original integral. Otherwise, we're just doing a substitution in a substitution. You should never need to do a substitution inside of another substitution. Substitution inside parts, no problem. Parts inside substitution, no problem. That's what this peanut butter cup. But this is a substitution inside of a substitution. That's just more substitution. There's one substitution that will handle them both. So there's no reason to switch from X to theta and then from theta to W when we can go directly from X to W. Questions? So it's at this point we should recognize, oh, hang on, let's not do this. The integral of X times the square root of 9 plus X squared dx. The substitution is W equals 9 plus X squared. Then dW is 2x dx. So a half dW is the x dx. So the integral of, so this is a W to the 1/2 power. So we add 1 W to the 3/2, 2/3. So we get a 1/3 W to the 3/2 plus C. And W is 9 plus X squared. So we'll get a 1/3 9 plus X squared to the 3/2 plus C. Good question. In this case, we pretended that we didn't notice that our original integral was substitution. We started doing a trigonometric substitution, found the theta integral was substitution. That needs to make us stop, go back, and do the problem as substitution. Good questions? One thing to note is that if you don't recognize that, if you don't remember that the theta integral being substitution means the x integral was also substitution, it's still okay. We can still proceed. We're just doing extra work. So notice, even if we don't notice, let's suppose that we didn't remember the substitution thing. And we're looking at the integral of, and we're back at, let's go back to this point. Let's go back to this safe point where it was secant to the third, tangent to the first. Remember, we've already ruled out the tangent substitution. So we're going to make the substitution W equals secant theta. So because our dW, this is how we're really deciding on what the substitution is. I've got enough parts to build a dW and have an even number of secants and tangents left over, or most importantly, an even number of tangents left over that I can convert to secants. I'm not going to have to in this case because there's only one tangent. So we're reading this as 27 times the integral of. Two of the secants are going to get integrated. So there's two of the factors. I'm going to split one of the secants off to be the dw. So my integral becomes 27 times the integral of w squared dw. So the integral is going to be 1/3 w to the third, so 9 w to the third plus c. Then we have to replace our w with secant. So it's 9 secant to the third and of course, at this point, we're not done because we're still looking at a theta antiderivative, and that's got to get turned back into an x antiderivative. So, no problem. Remember, we started with x is 3 tangent theta. And so I could solve this for tangent of theta. I don't remember what color I was using the other day. So this tells us that tangent of theta is x over 3. We could also say that theta is tangent inverse of x over 3, but we don't need that here because all we have is a secant of theta. So I'm going to look at the x over 3 and say this is opposite over adjacent and build a triangle. We want to get to the point where we don't have to draw the triangle. We can just think our way through it. But let's draw out our triangle. So opposite is x, adjacent is 3. The Pythagorean theorem tells us that the hypotenuse is going to be the square root of 9 plus x squared. Because of course it is. That's why we started this whole path in the first place. So the secant of theta is hypotenuse over adjacent. That's what we need to replace in our theta antiderivative. And if we simplify this, I've got 9 divided by 3 to the third, so that's going to be a 1/3. And the square root of 9 plus x squared to the third power is going to be 9 plus x squared to the 3/2 power. Read that radical as a 1/2 power. Question? How's everybody okay? Any questions? If your theta integral is a substitution, product power of trig function and it's a substitution, then your x integral was a substitution. Go back and do substitution. This is why I'm so concerned about finding out what products of powers of trig functions are not substitutions, because we're going to have to know those integrates with trigonometric substitution. How's everybody okay? This kind of thinking and backtracking tends to make us worry as students. But remember, you only have to be competent at trigonometric substitution for the next couple of months. After that, you're probably never going to have to do trigonometric substitution again, unless you find yourself in the position of teaching someone trigonometric substitution. It may have been different many decades ago, before we had computers that could easily just chug out integrals. But fortunately, instead of just using computers to chug out integrals, we would just look up integrals on a table. So what we would do, like I was there, what we did was we took all these trigonometric substitutions, we put them into categories. Then we learned how to algebraically break apart our integrals so they look like integrals that we could just look up in a table. This table would have to actually be in like a physical book because we didn't have computers to do all the work for us. Any questions? Remember learning your properties of logarithms? The log of a product is the sum of the logs of the factors. That is, log of xy is log of x plus log of y. The reason we had to do this is that it simplified the books that we had to write down all of our logarithms in. I don't have to include log of 6 in my book because we know log of 2 and we know log of 3. So before we had just calculators just tell us what the log of 6 is, like a bunch of spoiled brats. I'm just kidding. This is an important advantage. We would just know that the log of 2 was 0.301 and the log of 3 was 0.477. And so if I wanted the log of 6, I would just add those together. I can't remember what they were because it was too long ago, 15 seconds. That's way too long for me to remember a number. But now, if we want to know the log of 6, we could probably just ask our phone. Hey Siri, what's the log of 6? That was the natural logarithm. What's the common log of 6? And she's getting this from Wolfram Alpha, and it's got a decimal approximation that goes to a bonkers level. I mean, no one needs that many decimal places. Thank you, Siri. But before we had things like smartphones and graphing calculators or even slide rules, you wouldn't even have to look up the log of 2. You would just have to have been using it so much, you would just know that it's 0.301. Any questions? Remember rationalizing denominators? You don't get to write 1 over the square root of 2. You have to write it as root 2 over 2. Was anybody told that a radical in the denominator means an expression is not simplified? How many of you were told that? You had to rationalize your denominators. My big hope is that we'll get over this. The reason you don't want 1 divided by the square root of 2 is that if you have to work that out by hand, the square root of 2, the denominator, that's the non-repeating decimal. So I have to put 1.414, and then however many decimal places I want, into 1. And we're like, well, that's terrible. Let's write it as √2/2 so that we only have to divide by 2. That way, if we need more precision, we don't need to add more to the denominator. We just need to keep going with the numerator. But now, if I want to know what 1 divided by the square root of 2 is, you know who I'm going to ask. Any questions? Coming up with this function wasn't the point of the problem. And I'm not really sure that it was the point of the problem back when it might have been the point of the problem. How's everybody okay? Here's what we want to know about trigonometric substitution. This is just how to do trigonometric substitution. What trigonometric substitution is really about is quadratics. Right now, we've listed the tangent case as x squared plus a squared. But we have to take into account what if there's an x term in this quadratic. So it's no problem if we have, say, the integral of the square roots of x squared plus 9, the x. I took the x out of the front, so it's not a substitution. But what if there is an x term in our quadratic? So here we have the square root of x squared minus 4x plus 13. And we want to recognize this as a trigonometric substitution problem as well as just x squared plus 9. The important part is this x squared. Then the other important part is recognizing that x squared minus 4x plus 13 has complex zeros, and so that they should be the tangent case. So what we're going to do is we're going to read x squared minus 4x plus 13, and we're going to complete the square. I'm going to read x squared minus 4x plus 13 as x minus 2 squared plus 9. Then it will fit our tangent case. We're going to complete the square. So I have x squared minus 4x. Then we're going to think, what do we need to complete the square? Half of 4 squared is 2. So if I have a plus 4 here, then these first 3 terms can be written as x minus 2 squared. So I'm going to break 4 off of the 13 and write the 13 as plus 4 and a plus 9. That's what's left over. So our integral is the square root of x minus 2 squared plus 9. And now we have the integral above x squared plus 9 just shifted 2 units horizontally. Now we can see the tangent case. But instead of saying x equals 3 times the tangent of theta, I'm going to take x minus 2 and say that equals 3 times the tangent of theta. Dx is still 3 secant squared theta d theta, because the derivative of the 2 is 0. Any question? So now my theta integral will have the square root. This x minus 2, that's getting replaced with 3 tangent theta. So now it's going to look like a theta integral like we're familiar with. Oops. Dx. So in the radical, we've got the square root of 9 tangent squared theta plus 9. The trigonometric substitution thing means that is going to be 9 times secant squared. The square root of 9 secant squared is 3 secant theta. So then the trig sub thing happens. So in this case, we ended up with an odd power of secants without any tangents. So this is not a substitution problem. Now, we could just decide we're going to go look this up. But if you're going to look up the integral of secant cubed, don't do that. Just go back and look up the integral that you're actually interested in. If tables are going to come into play, don't bother substituting your way, looking at one part of the table, and then doing a bunch of work to get back out. If secant cubed is in the table, then the square root of x squared minus, or actually it'll be in this form, x minus h squared plus a k will also be in the table. Don't bother looking up the secant cubed, because we're not actually interested in that. We're more interested in the square root at the beginning. Any questions? Incidentally, we just found one of our product powers trig functions that is not substitution. How's everybody okay? So what we want to recognize is that trigonometric substitution is about quadratics. Of course, it's about quadratics. What's the big move? Using the Pythagorean theorem. 1 minus sine squared is cosine squared. 1 plus tangent squared is secant squared. Secant squared minus 1 is tangent squared. That's what's driving this whole process. That's what's getting us to the theta integral. So we can integrate that. Questions? Yes. The blue one? Yeah, that comes from this part here, the square root part. This is going to be the square root of 9 tangent squared plus 9. Then we can factor out the 9. And it'll be a tangent squared theta plus 1. And so that'll be the square root of 9 secant squared theta. That's the trig sub maneuver. That's the third piece that gets us into our theta integral. 3 parts in that first step, going from your x integral to your theta integral. There's the substitution determined by the case, x equals. There's the dx, because all x must become theta. And then there's the Pythagorean identity that you're going to use. Is everybody okay? It's kind of funny that a calculus book in 2021 has a section on look it up in a table. When we won't want to bother, because there's a lot of work, because the table can't display everything. So there's a section that just says, go look it up. But there are better ways of looking stuff up. Wolfram alpha. If you're going to look stuff up, just punch it into the calculating machine. Just get Wolfram alpha on the phone and say, hey, Wolfram alpha, what you got for this? And hopefully your teacher you only bought the student version of Wolfram alpha. And so it's like, are you done with your homework? Are you just checking, or are you getting the points? In which place should this click? Okay, I am just checking my work. And it'll be like, all right. It's like, hey, are you sure you're over 18? Yeah. You know what I mean? How's everybody okay? All right. Now, this seems like a lot to think about, but that's only because it's a lot to think about. It seems like a lot to remember, but that's only because it's a lot to remember. And you have to remember all of it all the time in perfect detail. We're setting the Wayback Machine to trigonometry, a class that sometimes you can get to calculus without having been in an actual trigonometry course. I've only been in a trigonometry course because I've taught trigonometry. But when I learned trigonometry, it was tacked on to algebra. So when I was going through calculus, I had to fill in a lot of the gaps in trigonometry. I did the same thing you all will do when you get to Calc 3. And you actually have to do a trigonometric substitution because you go into some other teacher's class. Then you can be like, Leach, you betrayed us. And I'll sit in my office and go, I heard that. Because I can hear it. That's one of my special abilities. I can hear when my students are cursing. I want you to know that just provides energy. That's what refills my monobar. So, because I did the same thing. I had to figure out a bunch of trigonometry that I didn't remember from my 3-week crash course in trigonometry tacked on to the end of algebra. And I do the same thing. I was saying, that jerk bull didn't teach me this trigonometry stuff. Or is it that I just don't remember? You know what I mean? All right. I don't really lose much in telling you that secant cubed should be done by parts. but it's going to require another integral that you don't know, that can't be done by parts. So eventually, at the core of these odd powers of secants without tangents, you need one to start. All right. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.